Okay, so I wanted to show you today how to graph variations of the sine function. If you need to do the same with the cosine function, the idea is the same. All you need to remember for this video and for other problems that require you to do the same is to remember what the basic shape of y equals sine x is. So that's the overall graph of y equals sine x. That's a picture from Bob Blitzer's pre-calculus book. And if you don't know what this thing looks like, right, that the sine function behaves this way from 0 to 2 pi, then your first step is to backtrack, right, go back and try and learn how we got to the shape of a graph. And in case you don't remember, we did that by creating a table x and y equals sine x, and then putting a bunch of angles like 0, pi over 6, pi over 4, all the way up to 2 pi, finding what the y values were for these, plotting those, in a graph, and then assuming that a smooth curve connected these. So that's how we got this shape, right? This basic shape of y equals sine x. But that's not what we're going to do today. What we're doing today is from that basic shape, find the graph of this more general function, y equals 3 sine 2x minus pi plus 5. So the first thing you have to notice is that, first of all, this plus 5 here is going to take this graph and bump it up 5 units. So instead of this being at 0, this is going to happen at 5, all the way up there at 5. Okay? So this is our vertical shift. So I'll say up 5 units. Okay? So our starting point will not be 0, 0, it will be 0, 5. Okay? So that's how I begin with that. So I'll go down a little bit. I won't even start graphing it because there's more information to get from this. But that's so far our first conclusion. This guy here is going to give me the amplitude. So the amplitude will be absolute value 3, which is 3. So if that were minus 3, the amplitude would still be 3 because there'd be the absolute value of minus 3. What does that mean? Well, that means that this length over here, rather than being 1, will be 3. So my function is going to be all the way stretched up vertically. So this is a vertical stretch by 3 units. Okay? And now to the most interesting part. Now I'll even do that in green. The inner portion of this is going to make a horizontal shift. Okay? So we're going to move this graph either to the right or to the left. So either it's going to do something like this, right? So all moved to the right, or something like this, all moved to the left, like that. So how do we find out, right? The first thing that I'll do is I want to find what's the x value that corresponds to the angle equal to 0. So that here, right, when y equals sine x, is when the angle equals 0. So I'll find out when is the angle equals 0, right? That's the beginning of my period because sine is periodic, so this is the beginning of my period. So when is 2x minus pi equals 0? So add pi on both sides, divide by 2. X equals pi over 2 is the beginning of my period. Okay? And then my other important information from the inside of the sine function is when does the period end? So here we go from 0 to 2 pi, so the period here is going to end when the angle is 2 pi. So when the angle is 2 pi, I'm saying 2x minus pi equal to 2 pi. So that's 2x, add the pi, so I get 3 pi, divide by 2, and that's 3 pi over 2. So that's, this guy here is what we call the phase shift. This is the phase shift. And this one here doesn't have a specific name, but we can use it to find what the period is, because the period will be the end of the period, so 3 pi over 2 minus the beginning of the period, which is the phase shift, which is pi over 2. So that's 3 pi over 2 minus pi over 2, so that's 2 pi over 2, so that's pi. Okay. So I think now we have all the information that we need to start graphing our function. Here's how we're going to do it. Right? I'll look at the beginning of my period, at the end of my period, and I'll even extend this Cartesian axis that I did over there a little bit. I'll make it a little lower too, because we're going to have that vertical shift we discussed. So I'll make it a little lower. That'll be x, that'll be y. So I'll start from x, right, from the green portion. So my phase shift is pi over 2. Here's what I'll do. I'll get this guy 3 pi over 2, and maybe what matters to me here are the quarter periods. Right? Because notice this, right? From 0 to 2 pi, the key points are spread out in between quarter periods, so 4 intervals. Each of those is 1/4 of the entire period. So I'll look at the period, I'll divide that guy by 4. And that will be the scale that I'll use. Okay? So I'll do then every 1/4 of a period, every pi over 4, I'll make a marking there. It's pi over 4, and then that's 2 pi over 4, which is pi over 2, right? And that's 3 pi over 4, and I'll keep doing that. So how many markings until I get to 3 pi over 2, right? So notice that 3 pi over 2 is the same as 6 pi over 4. So I need 6 markings to get to the end of my period. So 1, 2, 3, 4, 5, and 6. So 4 pi over 4, that's pi. 5 pi over 4. And then 6 pi over 4, which is the same as 3 pi over 2. So this is 6 pi over 4, and this is 2 pi over 4. So what that means is that this is going to be the beginning of my period, this is going to be the end of my period. Okay? This is my phase shift when my graph starts. The other important thing, they come from the vertical shift of 5 units and the amplitude of 3. So the vertical shift of 5 units, put like a 5 over there. And since the amplitude is 3, I have to also notice 8, which is 5 plus 3, and 2, which is 5 minus 3, because those will be the lowest and the highest points in my graph. So now I go. That's easy to see too, because the highest this could possibly be is when sine equals 1, and then that will be 3 times 1 plus 5 equals 8, right? So that's the highest point we could possibly have. And the lowest would be when sine equals minus 1, so that's 3 times minus 1 plus 5, which is minus 3, plus 5, which is 2. So that's the lowest it could possibly be. 2, the highest is 8. So that's my first point. So this guy, 5. I start from 5 because that's sort of the baseline. This is 0, and the original function, I'm bumping it up 5 units. Okay. Now 1/4 period to the right, I move up. Another 1/4 period to the right, I move down 1 amplitude. Another quarter period to the right, I move down. And another quarter period to the right, I move up again. I'm always moving up and down based on amplitude, and I'm always emulating the behavior of this gum. So this is what I'll have. Okay? Try to make it look a little bit nicer, but because my scale isn't perfect to begin with, my graph won't look perfect. What matters are the markings on the x and y axis, right, and my points obeying those markings. So this is it. This is how you get a precise graph for one period of one function. Now, one observation about phase shift. If you're using phase shift to graph this guy, maybe in an online homework platform or in some graphing utility that asks for the phase shift to graph, you may enter a wrong answer for the phase shift, right? Remember that this is the phase shift. You may enter a wrong answer for the phase shift and get the same looking graph. So here's what I'll do. I'll show you what the graph is supposed to look like. So this is the graph that we have over there. No, this is the one. This is the graph that we have, the purple one. And I've added the +5 at the end, you can see. So this is the graph that we just did. However, if you add, and I'm using GeoGebra now, I'm adding like a +a in the inside to cause the horizontal shift and therefore a different phase shift. What you have is that your graph moves to the right. So what I'm doing now is I'm making the a value of the phase shift change. Okay? So your graph is changing, and look at a on the top left. A is not the same as 0. The only way that we'd have the exact same function is when a equals 0. We don't, right? But still you see points where the graph overlap, just did. It's going to happen again now at 0. It's going to happen again. Happened again. Now it's going to match up again. So what does that mean? So if I stop the animation and just pick a value that's not 0, but that makes the graphs go inside. There you go. The graphs go inside now, and right now a is about 6.3. I imagine 2 pi is probably what we have. Is causing the graphs to look the same, but the functions are not the same, so the phase shifts are different, right? So +a, I'm adding +2 pi on the inside there. Because the function sine is periodic, right, we're getting the same graph, but the phase shift for those two is not the same. Because I've added 2 pi on the inside, 6.3 on the inside. So be careful when you're entering phase shifts. That may cause you to not understand why the answer is incorrect, even though the graphs look the same. So that's all I wanted to share with you today. Thank you for following along. And let me know if you have any other questions.